With a good understanding of reaction rates and enzyme-substrate interactions, we are now prepared to understand the principles behind steady-state kinetics. Let's start with a simple reaction scheme, where there is only one substrate or S molecule involved in the reaction and only one product, P. The first step in this process is the binding of substrate to form the ES complex. The rate at which this occurs relates to the rate constant, K1. Since substrate binding is a reversible process, the substrate might dissociate before the reaction occurs. For this reason, there is a double arrow associated with substrate binding. The reaction can go either way. The rate at which the ES complex dissociates to free enzyme and substrate is the rate constant, K-1. Let's make another assumption and say that there is only one catalytic step required to convert substrate to product. We'll call this rate constant K2, the rate of product formation. We want to eventually derive a rate expression for this whole process, and to simplify this process, we're going to make another assumption, that this catalytic step is irreversible, that is, that there is no K-2. Notice the one-way arrow associated with this step, indicating that it is indeed irreversible. If we examine the initial rate or velocity of this reaction as a function of substrate concentration, we find that the trend describes a hyperbolic plot. In these studies, keep in mind that the experiment is carried out with a constant amount of enzyme, only the substrate concentration varies. Notice the linear portion of the curve where activity relates to and changes with substrate concentration. This is an indication of first-order kinetics. It depends on the concentration of one reactant. Now notice the flat area of the curve, where the rate becomes independent of substrate. In other words, though the substrate concentration increases, the rate does not change. This would indicate zero-order kinetics. Because the velocity of the reaction does not reach any higher value than that represented by the flat portion of the curve, we call this the Vmax, or maximum velocity. Here the kinetics are zero order because the population of enzyme molecules are fully saturated with substrate. No more substrate can bind, no matter how much more we add. We're going to start to review the Michaelis-Menten model of kinetics, based on the very assumptions already made and using the simple reaction scheme already specified. We want to define an equilibrium dissociation constant associated with the binding of substrate to enzyme. We call this the Km, or Michaelis constant, and it is a measure of substrate affinity. Since it is a dissociation constant, a low Km means dissociation is disfavored and association is favored. This means that a lower Km means a higher binding affinity for substrate. Now let's use our knowledge of reaction rates to derive an expression for the rate of ES formation. Looking at our reaction scheme, we can see that the rate is equal to the rate constant K1 times the concentration of enzyme, or E, times the concentration of substrate, or S. This expression will represent the change in the concentration of ES over time. Next, we want to derive an expression for the rate of the disappearance of the ES complex. This will be equal to the decrease in ES concentration over time. From our reaction scheme, we can see that ES can disappear in two ways. Either the substrate will dissociate from the enzyme before forming product, or substrate can get converted to product. The overall rate of ES breakdown is then the sum of these two rates. The rate of the dissociation of ES is K-1 times the concentration of ES. The rate of product formation is simply K2 times the concentration of ES. In this model, we are using a steady state condition. That is, a condition in which there is no change in the concentration of ES over time. This can only occur if the concentration of substrate is much higher than that of enzyme. Note that this doesn't mean that all the enzyme molecules bind substrate molecules and never let go. Instead, it means that the enzyme will bind substrate and convert it to product, but there are so many substrate molecules present that as soon as the product is released, it binds more substrate. In other words, the enzyme remains saturated with substrate and spends no appreciable time in the free or unbound form. At this point, the rate of the formation of ES must be equal to its breakdown. We can now derive an expression of equivalence, substituting the rate expressions we derived earlier. Now we have an expression specifying steady state conditions.